And which one is this one?
It's way on the, yeah,
This one?
I think so.
Okay. Work.
Now, how do I advance?
Just click.
Okay,
Should be the easiest way to do it.
thank you so
Makes
much.
that work.
Can everyone hear me okay in the room? Can everyone hear me on Zoom?
Yes.
Cool. Thanks, everyone, for giving me the chance to share some research, and thank you for all the wonderful talks and discussions so far today. I know it's been a really exciting day with a lot to think about. The good news is this is a talk that's going to be mostly pictures, and I tried to streamline this talk a lot, and I am afraid actually I may have streamlined through my motivation slide. So earlier today, we heard a comment about how deep learning does work, and we're still unsure why it works. And so this talk is actually looking at a concept that's being explored in the area of classical deep learning, understanding where are solutions in your lost landscape, how do they relate to each other? And in particular, there's the concept of mode connectivity, in that if you have multiple minima in your landscape and there appears to be a barrier between two of your minima, is that barrier something you have to traverse to go from one minima to another, or is it possible to find more favorable paths of low loss connecting them? Yes, I did absolutely just go right through that slide. So the material I'm going to talk about today is in two papers that we have posted to the archive. So if you want more details, more information, and especially more references, they are all in those papers, and I encourage you to please look them up. I'm going to be talking about two different algorithms used in quantum machine learning. These are variational algorithms. The first is quantum circuit learning, which is basically just the analog of supervised learning for quantum circuits. So if you are familiar with the concepts of supervised learning and classical machine learning, these just translate directly to training a quantum circuit. You are training your circuit using a data set of labeled samples, and the training loss could be mean square error, could be binary cross entropy, and the training is done with a gradient descent algorithm, at least for the results I'm going to show in the rest of the slides here. Let's see what else we have here. Yes, and the main idea is that we have feature vectors, which we are going to use to prepare initial states, and we run our parameterized unitary on top of them. And then we extract our label or output from making measurements on our final state. The second workflow is called data-driven circuit learning. So this is an unsupervised training workflow. Slight differences between quantum circuit learning and data-driven circuit learning. For DDCL, it is unsupervised learning. We are using a parameterized unitary to prepare a target distribution P. Now, I don't have different input states. I fixed the input state. Commonly, it's the all zero state. And then I run my parameterized ansatz on top of that and sample from the final prepared state. And that's going to generate a distribution Q of theta. And the role of training is to make Q of theta approach P. So in the two papers that we have on the archive, what we are looking at are relatively small circuits. For our first paper on mode connectivity in the quantum circuit learning landscape, we only looked at circuits that had 3 qubits. And what we were using these 3 qubit circuits to do was fit a regression model that would be able to take an input value of X and predict Y, where Y is fitted using just a simple parabolic curve. And the ansatz design is just a very familiar layered ansatz where we have entangling gates and parameterized gates. We just chose 2 slightly different layouts for our entangling layers. In the second paper, where we look at mode connectivity in the DDCL landscape, we went a little more in depth in the circuit design. We looked at the brick layer ansatz, or we again looked at just the simple layered ansatz. And we started digging into the difference between different parameterizations, either using single rotation gates or just arbitrary 3 rotation angles. But the main idea for both of these studies, what we are going to do is once we have our models built and we have our training data set, we are going to train not one model, we're going to train models several hundred times. And what we're doing is we're trying to do a brute force exploration of our landscape. The motivation being that even with these very small circuits, we have multiple minima in our landscape, and we just want to find as many as possible. Once we have found them, here's an example of the distribution of the mean square error loss for our QCL training example. Once we have found multiple minima, we then down select them into a representative set of what we call relatively unique minima. Once we have done that, the goal is now to see how are these minima related to each other, and specifically, are they connected? And there are a couple of outliers. Again, this is only a subset of the data that we have trained. These are the absolute smallest circuits. The outliers are just where our training gets stuck on saddles. So that does happen. And here is a similar set of loss traces for our DDCL training workflow. Again, this is where we are just building multiple copies of our circuit models, and we are just training many times over. Just a quick note about the 2 different colors in the plot here. This is looking at the difference between our choice of parameterization for our circuit model, whether we just use the RY gate or the U3 parameterized gate. And again, training does get trapped on saddles. So, okay, so we have run a lot of training. Again, eliding over a lot of details about the training, but it is gradient-based descent. We tried multiple different optimizers. The training and all these results are generated in noiseless simulation just to get started in this proof of concept set of studies. But we've now done our brute force exploration of our landscape. We've down selected into our representative set of minima. And now we want to get an idea of how are these minima related. The first thing that we're just showing here is just some very nice visualizations of what does the landscape look like around our solutions. And this is just a straightforward projection onto a plane defined by 3 of our minima. And so now we're going to follow up using an approach proposed or implemented in this 2018 paper. Lead author is Draxler. And this paper is the one that really starts to study, do barriers pose a problem in neural network landscapes? Can they be navigated around? So what we did is we took the approach that they used for classical neural networks, and then we just applied them to our quantum circuit landscapes. And that analysis is an algorithm known as the nudged elastic band. And so what the nudged elastic band algorithm, it's a search for low loss paths in our higher dimensional lost landscape. The workflow in a nutshell is this: we have 2 minima, which are represented by the red and the blue points. The starting point for our algorithm is we just draw a straight line connecting these 2 minima. That would be our first guess of how to go from minima A to minima B. Most likely that will go up and over a very large barrier. The next step is now we want to deform this path away from just a straight line cut, treating it like it was an elastic band. We're going to set up a discrete number of points along that path, and we're going to update those positions and try and optimize it so that our points along that path sit along low loss points. And so down here, what I'm showing is how the nudged elastic band can improve our navigation from one minima to another in the QCL landscape. So the thick black line, this is our initial guess, just a straight line path from one minima to the next. And then the blue line, and there's also technically a red line there. These are showing the final positions or the loss along our final nudged band, and also the best performing nudged band, where best performance is quantified by minimum area under the curve. But sometimes when we are looking into our lost landscapes, our initial guess can actually be pretty great. Just making a straight line cut between two minima can yield a very flat landscape. And that tends to occur when our solutions sit in ravines, these just areas of low loss connected by straight paths. In our first paper, where we looked at mode connectivity for the quantum circuit learning landscape, we saw that sometimes these ravines correspond to dropout stable patterns in our parameterized circuits. What I'm showing here are examples of ravines that we found in the DDCL landscape itself. For the DDCL landscape, this is the study where we looked into how does different parameterizations of our circuit affect the trainability and mode connectivity. One thing that we notice is that the choice of parameterization does make it a lot easier to find low loss paths connecting our minima. It's not guaranteed. And again, since these are relatively small circuits for both of our studies, the DDCL study, we looked at 2, 4, and 6 qubits. What we start to see is that for small circuits, it is we have more success in finding low loss paths connecting our minima. Unfortunately, this isn't necessarily true for larger circuits. As our circuits get larger, our minima tend to be separated by these wide flat barriers. So while this is promising work just to get started, showing that it is possible to observe mode connectivity in variational landscapes, there are a lot of open questions that still need to be answered. And just a quick wrap up of just some of the open questions that we have. We know that in our variational landscapes, we have multiple minima. And some of these minima can be connected by low loss paths. We found that for several examples of small circuits. We found it for two different variations of quantum circuit training, either supervised training or unsupervised training. But the question is, how can we now design circuits to have robust connectivity? And that could be robust in terms of increasing circuit size or depth, or more importantly, robustness against noise. That is absolutely an open question and something that we're actively investigating right now. But again, this gets to the motivation slide that I cut out of here. If we know that mode connectivity exists, how can we use it? How can we further exploit this? And one thing we can do is that connected modes, well, each mode corresponds to a different set of parameters which have good performance on our particular training problem. So if we can easily find multiple modes in our landscape, we can easily generate multiple copies of different trained versions of our model, which have comparable performance on our training data. And so this, we're hoping to leverage this in building larger models, first by just building ensembles of our parameterized circuit models as a start. And then just connecting back also to robust circuit design. Is there anything in our ONSOF design that may facilitate connectivity, or even worse, is there something that could impede it? That is ongoing work. So that is all for my talk. This work is done with a number of collaborators, a number of really great students, from both the SULI intern program and also Duke University, as well as researchers at Oak Ridge. Again, these are the archive identifiers for these papers. If you want any further details or more pictures, please check them out. And yeah, thank you for your attention. I'll be happy to take questions now.
One question, since we're a little bit behind. I'll ask you one quickly. Do you expect to have more ravines or more conductivity as the depth gets on larger of your circuits?
Based on our first study where we saw that ravines can be connected to dropout stable patterns as the circuits get larger. If there's more dropout patterns in your circuit, we hope to see more ravines. The question is, are those ravines easy to find or not? The big problem is just scaling up this brute force surge. It's not going to scale as the circuits get larger and deeper, just trying to train over and over and over again and really find unique minima. So,
We should talk. I'm
Yeah.
very interested.
absolutely.
Any other quick questions? Probably not. We're way behind. So we're, we have one more talk between you guys and dinner. So let's do the last talk. Is there a speaker on Zoom?
Yes, hello.
Awesome.
Can everyone there hear me?
We can hear you. We are sharing your screen.